We often hear that larger neural networks are more capable, leading to better performance across many tasks. But isn't there a critical point where they just become too slow and prohibitively expensive to actually train and deploy?
That tension between wanting immense model capacity and needing practical computational efficiency is absolutely a fundamental challenge in scaling neural networks. What if we could achieve the best of both worlds simultaneously? Think of a neural network like a vast library, where each parameter is a bookshelf or a specific book. The more shelves or books, the more information it can potentially store and retrieve. But a larger library often means more time and effort to find the right book.
So, a model with more parameters can potentially learn and store more complex patterns and facts. But when it's processing a new input, it has to activate and consider all those parameters, which slows everything down.
Right, and this is where the library analogy starts to break for MOE. Instead of searching the whole library for every query, MOE intelligently dispatches you directly to the relevant section, or even a specific expert librarian. It's not about less information, but smarter access. Exactly. This seminal paper introduces a powerful solution called conditional computation. The core idea is that instead of every part of the network working on every single input, only the relevant parts activate and contribute on a per-example basis.
Per example basis. So, if I ask the model about cooking, only the specific neurons or sections focused on culinary knowledge wake up, and all the physics or history-related neurons stay dormant? That's a huge shift.
That's a perfect intuition. Imagine a massive, highly specialized consulting firm with experts in every field imaginable. When a client comes with a specific problem, you don't send the entire firm. You dispatch a small, expert team precisely tailored to that client's unique needs.
So, the firm possesses immense collective knowledge and capacity, but for any single project, only a small, relevant fraction of its resources are active. This makes it incredibly efficient despite its overall size. I see the parallel now. One key difference, though, is that unlike a human firm, our neural network's dispatcher, the gating network, isn't a fixed HR department. It continuously learns and adapts which experts to pick, becoming more efficient with experience. The paper formalizes this approach as a sparsely gated mixture of experts layer, or MOE. This layer is composed of a collection of specialized experts, each typically a small, independent feed-forward subnetwork. And sparsely gated explicitly tells us that only a few of these experts are actually engaged at any one time. It's not about averaging everyone's opinion, but selectively choosing the most qualified few, just like the consulting firm.
Precisely. The crucial innovation here is a trainable gating network. This network is typically a small neural network itself, often a simple linear layer, that takes the input representation and outputs a score for each expert. For any given input, it learns to assign higher scores to the most relevant experts. It then uses a mechanism, commonly a top K selection like picking the top 2 highest scores, to decide which experts to activate and how strongly each should contribute.
So the model isn't just specialized, it actually learns how to route tasks to its specialists. That's incredibly powerful. It sounds like a dynamic, adaptive routing system rather than a fixed one.
This conditional computation approach enabled them to claim achieving greater than 1,000x improvements in model capacity with only minor losses in computational efficiency. That represents an absolutely transformative leap in what's possible for neural network scaling.
1,000 times the capacity for only minor efficiency losses? That's what they were hinting at with outrageously large neural networks in the title. It sounds almost too revolutionary to truly grasp.
This is particularly vital for large language models, where model capacity is critical for absorbing the vast quantities of knowledge available in the training corpora. The more parameters, the more deeply and broadly a model can store knowledge about the world.
So, it's about providing the model with an absolutely enormous brain to accumulate facts, understand nuances, and learn complex relationships, while still keeping it nimble and quick enough to use that brain effectively during inference.
The original paper implemented MOE applied convolutionally between stacked LSTM layers, but the core concept of conditionally activating subnetworks is highly generalizable. Today, we primarily see MOE integrated into the feed-forward blocks of transformer layers.
So it's not a brand new network architecture itself, but a powerful modular layer type that can be strategically inserted into existing architectures, like the transformer models we thoroughly explored in TCM 213002.
Precisely. This foundational idea of sparsely gated experts is no longer just theoretical. It's now a cornerstone for building many of the largest, most performant language models we use today.
I'm really curious to see how this original idea from 2017 actually manifests and delivers on its promise in today's state-of-the-art large language models. Let's look at a concrete example.
Fast forward to January 2024, and we see the practical realization of this vision in models like Mixtral 8x7b, a sparse mixture of experts, SMO, language model. Mixtral builds directly on that 2017 MO concept, pushing its capabilities further.
Mixtral has certainly garnered significant attention in the LLM landscape. This makes it a very current, real-world example of conditional computation delivering on its promise at a truly massive scale.
The paper clarifies its architectural integration. Mixtral has the same architecture as Mistral 7b, with the difference that each layer is composed of 8 feed-forward blocks, i.e. experts. This is where the MOE magic happens within the transformer.
So in every transformer layer, instead of just one large, dense feed-forward network processing all tokens uniformly, there are now 8 distinct smaller and specialized networks acting as experts. That's a direct, elegant application.
Crucially, for every token at each layer, a router network selects 2 experts to process the current state and combine their outputs. To be more specific, the router network, trained alongside the experts, processes the token's representation and generates a sparse distribution over the 8 experts, essentially giving each expert a ticket value. It then deterministically selects the 2 experts with the highest ticket values. Their outputs are then combined, typically by summing them weighted by those same ticket values, a learned weighted average, essentially.
Every token at each layer. That's incredibly fine-grained control and allows for extreme specialization. And it explicitly says it picks 2 experts, not just 1. Is there a reason for that specific number?
Selecting 2 experts provides a sweet spot. It allows for richer, more nuanced processing and better information synthesis than relying on just 1, while still maintaining high sparsity and significant computational savings compared to using all 8.
It's like getting 2 highly qualified specialist opinions on a complex problem, and then intelligently combining their insights. This makes the decision more robust and comprehensive, but still avoids involving the entire committee.
Exactly. Though unlike human experts who might debate or negotiate, in MOE, the combination is a precise mathematical operation, often a weighted sum, where the gating network provides the weights. There's no subjective deliberation, just a deterministic, learned blend. And this expert selection is entirely dynamic and context-dependent. Even though each token only sees 2 experts, the selected experts can be different at each time step. The routing isn't static or predetermined, it adapts.
So within a single sentence, as the model processes token by token,
the underlying active computational path can shift dramatically, potentially engaging dozens of different expert combinations across its length. That's true adaptability.
This is where the MOE paradigm truly shines. Each token has access to 47B parameters, but only uses 13B active parameters during inference. It skillfully leverages the model's vast knowledge without the full computational burden of a dense 47B model.
Wow, that's a more than threefold reduction in active compute compared to its total parameter count. So the model contains an enormous 47 billion parameters of learned information, but it processes each token with the efficiency of a 13 billion parameter model.
And the empirical results are profoundly compelling. Mixtral outperforms or matches Llama 270B and GPT 3.5 across all evaluated benchmarks. This isn't just about efficiency, it's about achieving state-of-the-art performance with that efficiency.
So not only is it dramatically more efficient in its active compute for its effective parameter count, but it's consistently competitive with or even superior to much larger, densely activated models like Llama 270B. That's a strong argument.
The paper highlights specific areas where it excels. Mixtral vastly outperforms Llama 270B on mathematics, code generation, and multilingual benchmarks. This strongly suggests the expert specialization is working as intended, leading to superior capabilities in targeted domains.
That's a very clear indication of the power of specialization. It implies that having dedicated math experts or code experts within the model allows for a level of focused proficiency that a generalist model might struggle to achieve.
A critical pitfall is confusing Mixtral's total parameter count of 47B with its effective size during inference. While it contains 47B parameters, its computational cost per token is closer to that of a 13B dense model. Training costs are also different.
So, we absolutely shouldn't compare Mixtral 8x7B directly to a dense 47B model in terms of required compute for a single forward pass. Instead, it's more accurate to consider its active parameter count when assessing inference efficiency. That's a crucial distinction for understanding its real-world application.
Mixture of Experts stands as a highly effective tool for scaling neural networks, enabling access to vastly larger learned knowledge bases without the proportional computational burden during inference.
It's now crystal clear why this technique is so impactful. But what are the catches? It can't be all upside, right?
While MOE brings immense benefits, it's not without its challenges. One major one is load balancing. If the gating network doesn't distribute inputs evenly, some experts might become overloaded or underutilized, which can hurt performance and efficiency.
And even though active parameters are reduced during inference, the total 47 billion parameters still need to be stored in memory. So while compute is saved, the memory footprint can still be substantial, especially during training or when deploying many such models.
Exactly. To counteract the load balancing issue, during training, an auxiliary loss is often added. This loss function incentivizes the router to distribute tokens more evenly across the experts, ensuring that all experts get utilized and contribute meaningfully, preventing underutilization or overload. And the routing mechanism itself adds a small computational overhead, and the optimal number of experts and how many to activate, like the top 2 in Mixtral, are often empirically determined, requiring careful tuning for specific tasks.